Stochastic volatility models are those in which the variance of a stochastic process is itself randomly distributed. They are used in the field of mathematical finance to evaluate derivative securities, such as options. The name derives from the model's treatment of the underlying security's volatility as a random process, governed by state variables such as the price level of the underlying security, the tendency of volatility to revert to some long-run mean value, and the variance of the volatility process itself, among others. Stochastic volatility models are one approach to resolve a shortcoming of the Black-Scholes model. In particular, models based on Black-Scholes assume that the underlying volatility is constant over the life of the derivative, and unaffected by the changes in the price level of the underlying security. However, these models cannot explain long-observed features of the implied volatility surface such as volatility smile and skew, which indicate that implied volatility does tend to vary with respect to strike price and expiry. By assuming that the volatility of the underlying price is a stochastic process rather than a constant, it becomes possible to model derivatives more accurately. Basic model. Starting from a constant volatility approach, assume that the derivative's underlying asset price follows a standard model for geometric Brownian motion, whereas the constant drift of the security price is the constant volatility, and is a standard Wiener process with zero mean and unit rate of variance. The explicit solution of this stochastic differential equation is the maximum likelihood estimator to estimate the constant volatility for given stock prices at different times as its expectation value is. This basic model with constant volatility is the starting point for non-stochastic volatility models such as Black-Scholes model in Cox-Ross-Rubinstein model. For a stochastic volatility model, replace the constant volatility with a function that models the variance of. This variance function is also modeled as Brownian motion, and the form of depends on the particular SV model under study, where an ism functions of an is another standard Gaussian that is correlated with constant correlation factor. Heston model. The popular Heston model is a commonly used SV model, in which the randomness of the variance process varies as the square root of variance. In this case, the differential equation for variance takes the form, whereas the mean long-term volatility is the rate at which the volatility reverts toward its long-term mean, is the volatility of the volatility process, and is, like, a Gaussian with zero mean and standard deviation, however, and are correlated with the constant correlation value. In other words, the Heston SV model assumes that the variance is a random process that exhibits a tendency to revert towards a long-term mean at a rate, exhibits a volatility proportional to the square root of its level, and whose source of randomness is correlated with the randomness of the underlying price processes. There exist few known parametrization of the volatility surface based on the Heston model as well as their arbitraging methodologies. CEV model. The CEV model describes the relationship between volatility and price, introducing stochastic volatility. Conceptually, in some markets volatility rises when prices rise, so, in other markets, volatility tends to rise as prices fall, modeled with. Some argue that because the CEV model does not incorporate its own stochastic process for volatility, it is not truly a stochastic volatility model. Instead, they call it a local volatility model. SABR volatility model. The SABR model describes a single forward under stochastic volatility. The initial values are the current forward price and volatility, whereas are two correlated Wiener processes with correlation coefficient. The constant parameters are such that the main feature of the SABR model is to be able to reproduce the smile effect of the volatility smile. GARCH model. The generalized autoregressive conditional heteroscedasticity model is another popular model for estimating stochastic volatility. It assumes that the randomness of the variance process varies with the variance as opposed to the square root of the variance as in the Heston model. The standard GARCH model has the following form for the variance differential. The GARCH model has been extended via numerous variants, including the NGARCH, TGARCH, IGARCH, LGARCH, EGARCH, GJR-GARCH, etc. Strictly, however, the conditional volatilities from GARCH models are not stochastic, since at time t the volatility is completely predetermined given previous values. Three-halves model. The three-halves model is similar to the Heston model, but assumes that the randomness of the variance process varies with the form of the variance differential is. However, the meaning of the parameters is different from Heston model. In this model, both mean reverting and volatility are variance parameters, as stochastic quantities given by and respectively. Chen model. In interest rate modelings, Chen in 1994 developed the first stochastic mean and stochastic volatility model, Chen model. Specifically, the dynamics of the instantaneous interest rate are given by following the stochastic differential equations. Calibration and estimation. Once a particular SV model is chosen, it must be calibrated against existing market data. Calibration is the process of identifying the set of model parameters that are most likely given the observed data. One popular technique is to use maximum likelihood estimation. For instance, in the Heston model, the set of model parameters can be estimated applying an MLE algorithm such as the Powell-directed set method to observations of historic underlying security prices. In this case, you start with an estimate for, compute the residual errors when applying the historic price data to the resulting model, and then adjust to try to minimize these errors. Once the calibration has been performed, it is standard practice to recalibrate the model periodically. An alternative to calibration is statistical estimation, thereby accounting for parameter uncertainty. Many frequentist and Bayesian methods have been proposed and implemented, typically for a subset of the above-mentioned models. The following list contains extension packages for the open-source statistical software that have been specifically designed for heteroscedasticity estimation. The first three cater for GARCH-type models with deterministic volatilities. The fourth deals with stochastic volatility estimation. RuGARCH, ARFIMA, in mean, external regresses and various GARCH flavors, with methods for fit, forecast, simulation, inference and plotting. FGARCH, part of the R metrics environment for teaching, financial engineering and computational finance. BayesGARCH, Bayesian estimation of the GARCH model with student T innovations. SticVol, efficient algorithms for fully Bayesian estimation of stochastic volatility models via Markov chain Monte Carlo methods.